Okay. So here is example 3C. All right, 10 fair dice are rolled. All right, so let's let xj be the result of the roll of the jth die. All right. Now, find the approximate probability that the sum obtained, so my sum, I'll let S, is the sum of all 10 rolls, that the sum obtained is between 30 and 40 inclusive, so we want non-strict inequalities. So I want to get an approximate number for this probability. And they want us to use the central limit theorem. And you might think to yourself, well, that's n equals 10. Is 10 large? Does the central limit theorem even apply when n is 10? Well, that's a good question. And, you know, it's as phrased there and in the context of our class, it's not really one that we can answer mathematically. It's, in some sense, subjective. Is it large enough so that your approximation is good enough? For what purpose? How good is good enough? So it can be a little subjective, but also the problem is that we don't have more advanced theorems in a class like this to be able to judge, you know, how good the central limit theorem is. If you need the central limit theorem to judge how good the law of large numbers is, then you need something even stronger to judge how good the central limit theorem is. So we're just going to take it on faith, or take it for granted that when they want us to use the central limit theorem in the book, that it's a good idea to do that. So we'll use it here, even though n is 10. That's fine. We'll see what happens. All right, so we use the central limit theorem, and the central limit theorem, again, I'm just going to say that S is approximately normal in distribution. So S has approximately, that was supposed to be a D. S has approximately the same distribution as sigma, sorry, not sigma, mu there, mu plus sigma z, where z is a standard normal, mu is the expected value of S, and sigma squared is the variance of S. Let's figure out what those are. The expected value of S is 10 times the expected value of any one of those rolls. You roll a die, standard, fair, six-sided die, the expected value is 3.5. 7 halves. Well, put 3.5, so 35. Okay, and what's the variance? Well, the rolls are independent, so the variances add up. So it's the variance of x1 plus the variance of x2, and so on. They all have the same variance, so it's 10 times the variance of just x1. And we have to go back and look. We calculated what the variance is in one of the examples a while ago. If you go back and look that up, you get 35 twelfths. Okay, so then what's that? 6 and 5, right? So 350, 175 over 6. Okay. So 35 is my mu, and this is my sigma squared. All right. So S has approximately the same distribution as 35 plus the square root of 175 over 6 times the standard normal. All right, now let's approximate them. What's the probability that 30 is less than or equal to S is less than or equal to 40? Well, again, now S is discrete, whereas Z is continuous. So I need to use my continuity correction. So I'm going to say that's approximately equal to, with the continuity correction, and I have greater than or equal to here, I'm going to replace 30 with 29.5. And I'm going to replace S with 35 plus root 175 over 6 times Z. And I'm going to replace 40 with 40.5. Okay. So this gives me what? The probability that negative 5.5 is less than or equal to root 175 over 6z, which is less than or equal to 5.5. So that's the probability that root 175 over 6 times absolute value of z is less than or equal to 5.5, which is the probability that absolute z is less than or equal to 5.5 times the square root of 6 over 175. Okay. We can calculate, what is that then? This now, if you get out the calculator, is approximately 1.0184. So this is going to be approximately, like we did before when we looked at the graph of the bell curve, 2 times phi of 1.0184 minus 1. And then you get out the table to approximate the phi value, and this is approximately 0.692. So about a 70% chance you roll 10 dice, and you want to sum between 30 and 40 inclusive. You have approximately a 70% chance. They don't show it in the book, and I guess I can leave it as an exercise that you'll probably need to know some coding or some way to calculate these things, or maybe just Google a nice tool online. But it might be a nice exercise to calculate the exact probability. Answer the question of, is the central limit theorem a good approximation here when n is only 10? Central limit theorem says the probability is about 0.692. What is the real probability? How close is that? So that might be a nice exercise if you want to explore that. Okay, here's example 3D. All right, let's let x1 through x10 be independent random variables. Each uniformly distributed over 0, 1. So if they all have the same distribution, then they're not only independent, they're IID, which is what we need. Calculate an approximation to the probability that the sum, as j goes from 1 to 10, of xj is greater than 6. All right, so this is very much like our previous problem, right? If I call this S, or call it that is S10, right, in our notation, then I'm applying the central limit theorem with n equals 10 again. All right, so S10 has approximately the same distribution as mu plus sigma z, where mu is the expected value of S10, which is 10 times the expected value of any one of the x's. They're uniform 0, 1, so expected value is a half. 10 times a half is 5, so mu is 5. Sigma squared is the variance of S10. They're independent, so variances add, so it's 10 times the variance of any one of them. The variance of a uniform 0, 1 is 1/12. So this is sigma squared is 5, 6. So sigma is the square root of 5, 6. So S10 has approximately the same distribution as 5 plus the square root of 5, 6 times z. And I want to approximate the probability that S10 is greater than 6. Again, now S10 is what? Well, it's a sum of uniforms. So it's continuous. And of course, z is continuous, so there's no need here for a continuity correction. So we can just say this is approximately the probability that 5 plus root 5 over 6 times z is greater than 6. So that's the probability that z is greater than 1 divided by root 5 over 6, so root 6 over 5. So that's 1 minus phi of root 6 over 5, and you get out a little table and figure out what that is. And you get 0.1367. Okay. All right, last example. Example 3E, an instructor has 50 exams that will be graded in sequence. The times required to grade the 50 exams are independent. So let's let xj be the time it takes to grade the jth exam. And we have x1, x2, up to x50. They are independent. All right, they're independent with a common distribution. So they're also identically distributed. With a common distribution that has mean 20 minutes. Okay, expected value of x1 is 20. And standard deviation, 4 minutes. Now this time the book got it right. The standard deviation is 4 minutes, which means the variance is 16 minutes squared. So the variance is 16. Approximate the probability that the instructor will grade at least 25 of the exams in the first 45 minutes. So A is the event that instructor grades at least 25 exams in the first 450 minutes. And I want to approximate the probability of A. Okay, so first thing I need to do is connect the event A to the random variables in question, and then the second thing to do is apply the central limit there. All right, so how do we make the connection? Well, if I look at the first 25, the question is phrased in sort of an odd way, but it's really saying that if you look at the first 25 exams, how long is it going to take the instructor to grade them? Will it take the instructor less than 450 minutes or more than 450 minutes? Right. So if Sn is the sum of the amount of time it takes, well, the sum of the first n x's, then one way to interpret Sn is it's the time to grade the first n exams. And so A is just the event that S25, the time it takes to grade the first 25 exams, is less than 450. All right. Oops. You can say less than or equal to, it won't matter. All right, so now we want to use the central limit theorem. So S sub 25 is approximately normal. So it's approximately mu plus sigma z, where mu is the expected value of S25. All right, so that's 25 times the expected value of x1. The expected value of x1 is 20. So mu is 500. Sigma squared is the variance of S25, which is 25 times the variance of x1. The variance of x1 is 16. 25 times 16 is 400. So sigma is the square root of 400, so sigma is 20. I keep forgetting my d there. So S25 has approximately the same distribution as 500 plus 20 times a standard normal. All right, so the probability of A is the probability that S25 is less than or equal to 450. And we need a continuity correction. Depends if S25 is discrete or if it's continuous. Well, S25 is either discrete or continuous, as the same quality as the x's. So what are the x's? X1 is the amount of time it takes in minutes to grade the first exam. This is not a discrete random variable, right? It might take 4.5 minutes. It might take, 4 1/3 minutes. So it's continuous. We don't know the distribution, but whatever distribution it is, it's got to be a continuous distribution. So S25 is continuous, so we don't need a continuity correction. All right, so this is now going to be approximately equal to the probability that 500 plus 20z is less than or equal to 450. Okay, so that's the probability that 20z is less than or equal to -50. So the probability that z is less than or equal to -5/2, which is, well, it's phi of -5/2, or -2.5, but you can't get the negative values off the table. So we want to rewrite that as 1 minus phi of +2.5. Now we can look on a table to approximate that. And we get that it's approximately 0.006. So 0.6% chance that he's going to get that much grading done. And that really goes against my intuition, because I would have thought the chance was a lot lower. And it's weird to make jokes when there's nobody here to laugh at them. But that was my attempt to complain about the torture of grading, which sometimes is very nice, but most of the time it's not a fun activity. But that's it for the examples. That's it for the main line of the material. I'm going to get some homework problems up for you guys to do. Maybe if I have time, I'll put some supplemental material, because I know there's a lot that's unsaid, and I know there's a lot of you in the class who are very curious about things. Like, how can we judge the accuracy of the central limit theorem? What are these weird conclusions in the two big theorems? They look very strange and unlike any kind of limits that you're used to seeing. So there's a lot of really cool and sort of deep stuff, but not so deep, that I can explain to you. But if I were to do that, it's just going to be optional supplemental videos, handouts, if I have time. It won't be anything that you'd be required to learn or study. But if I get any of that done, I'll put it up and I will let you know. And that's it. Have fun with this stuff and email me anytime with any questions. I will be quick to respond, typically. All right. Thanks, guys.